Hey, I'm Eric, and I wanted to tell you about SalmonBot. But first, what's a salmon ladder? A salmon ladder is an obstacle that was popularized by American Ninja Warrior. It requires coordination to give yourself enough upward momentum to be able to pick up the bar and place it on the next rung. I chose to model the robot as a 5-link planar robot. The torso serves as a floating base with an X, Z, and angular position. The shoulder is connected to the torso with a revolute joint, and the hands are connected to the shoulder with a prismatic joint. The thighs and lower legs are connected with a revolute joint at the hip and the knee. I'm using a multi-body plant from Drake to compute the dynamics for my model. I chose to apply hybrid trajectory optimization with direct transcription. For the decision variables, I'm using Q, Q dot, Q double dot, the joint efforts, the contact force, and a per time step dt. While Q double dot isn't strictly necessary, it's helpful for writing out the implicit manipulator equation constraint and the integration constraint. For the cost, I'm using a per time step quadratic penalty on control effort and joint velocity. In order to use hybrid trajectory optimization, we need to define modes, guards, and reset maps. The first mode is in notch. In this mode, the hand and the bar are constrained to stay in contact with the ladder, meaning that we can apply contact forces. The next mode is hook range. In this mode, the bar is broken contact with the ladder, so no contact forces are allowed. The hand and the bar can move within a confined Z range, but they are only confined in the X direction by the upright. Finally, we have the hook clear mode, where the hand and the bar can move in the Z direction, but it must not enter the region where it may collide with the hook. Guards are the conditions that define when we can transition between modes. For my formulation, they are purely a function of hand position. We can always transition from in notch to hook range, and we can transition from hook range to hook clear in the regions where there is overlap between the modes. Finally, I'm using identity reset maps. As far as I'm aware, the only implication of this choice is that we're required to reach the in notch mode with 0 hand velocity. Using a horizon of 21 time steps per rung, we can define the following mode sequence. Now that we've formulated a problem, we can hand it to SNOP to find the optimal trajectory. And here's what it came back with. I optimized for 2 cycles and added consistency constraint between the start and end of the second cycle. With the same control limits, we can even skip a rung. I tried lowering the maximum arm force to see if I could discover more coordination between the legs and arms, but I wasn't able to get anything interesting. In these plots, looking at the control effort and states for the skip rung case. Looking at the arm effort and the Y component of the contact force in the lower left plot, we can determine the vast majority of the effort is coming from the arms. It's also not clear to me why the lower legs are fluttering, as I would have thought the per time step costs would damp out vibrations if they're not beneficial. Initially I was planning on taking a contact implicit approach, but I learned that Drake only provides contact gradients for limited geometries. I learned about how difficult it is to do this in general. I also found that making optimization problems smaller tended to yield better results. I tried using graph of convex sets to avoid predefining a mode sequence, but it wasn't obvious how I could specify a trajectory within a mode. Thanks for listening.